We can finish.
Okay, so now we're going to talk about non-symmetric Macdonald polynomials. But sadly, there's a lot of work to get to the point where I get to talk about anything new, because we're going to have to go back to the symmetric for a minute. But let me first define the non-symmetric world and the non-symmetric Macdonald polynomials. So first of all, non-symmetric polynomials, what are they? They're just polynomials, Laurent polynomials. There's nothing particularly non-symmetric about them. They're just polynomials. Um, and so now the bases are indexed by any integer vector. If you have n variables, an integer vector of length n. And just like I'm trying to kind of give you an analogy to what I started with the Schur functions, but now I'm in like this space of polynomials, bases indexed now by integer vectors, not partitions. And there's also an inner product on this space. Here it is. I don't think that you need to belabor it because it won't really be that relevant, but it exists. And then also what exists is an analog to Schur functions. The difference here is that they're not self-dual. The two sort of like Schur bases for this space of non-symmetric Laurent polynomials are called key polynomials and atom polynomials. And they have all of the beautiful features that Schur functions have. They have combinatorics, representation theory, geometry, and you could also use these divided difference, the isobaric divided difference operators to generate them. But most importantly for our talk is going to be that if you take the Weyl symmetrization, which if you want to think of it as this operator indexed by the longest permutation, that's not really usually how we think of it, but it is that. If you Weyl symmetrize an atom, it's either a Schur function or zero. So that means that if you have a function, a polynomial that's atom positive, and you Weyl symmetrize it, you get something that's Schur positive. So we think of it as a strengthening of Schur positivity if you have something that's atom positive that's non-symmetric. So that's kind of the key. But otherwise, these are two bases, very, well studied, and that doesn't mean they're easy, but they're still unknown questions, but whatever. They do have all the nice features of Schur functions. So the non-symmetric Macdonalds are, well, actually Cherednik's, because they're defined using his operators, but whatever, we're going to think of them in the very same way that we think of Macdonald's and Schur functions, which is that they are unitriangularly related to monomials now and orthogonal with respect to this scary inner product with q's, now q's and t's, just like before, that reduces to the other one when actually here you have to sort of take a limit of q goes to infinity and t goes to infinity. But in any case, the idea is that like this does specialize to an atom, and you can compute an example, although we're lucky to have ChatGPT. These people had a lot stronger constitutions than us and probably did this by hand. But whatever, if you compute one, you're going to get something like you see. Again, it's not a positive sum. We probably wouldn't expect it to be because we already knew that the Macdonald wasn't a positive sum. But anyway, it looks like this. Sorry, I forgot what I'm doing next. Oh yeah. So a couple things about them. Why did they arise? Well, this was, as I said, Cherednik introduced some operators in the double affine Heck algebra. These are polynomials which are eigenfunctions of his operators. So that's why I say that there is a whole contingent of people who are working in the non-modified side. And now so am I have to admit. But anyway, whatever. So the other thing about these polynomials is that you can Heck symmetrize them to get a usual Macdonald. And that's sort of pretty important, I think, in the way that my work has gone in my life, because Cherednik had his work for the non-symmetric Macdonalds, but one of the things that Knopp and Sahi did was that they discovered that you could come up with these recurrences for the non-symmetric Macdonalds that did not exist for symmetric Macdonalds. So they were able to prove nice, beautiful identities about non-symmetric Macdonalds and then hex symmetrize to get results about symmetric Macdonalds. So that's kind of a theme in my own work, which is like sometimes when you go to the like more complex setting, you get these tools that are not available to you in the restricted setting that help you even when you project back down. Anyway, that was some of the stuff that was going on. I've kind of forgotten. Oh, okay. But here's like the big question in my, related to this talk in my life, which is we already hopefully are convinced now that the modified Macdonald polynomials are these really great things that have the beautiful representation theory, the beautiful tableau combinatorics, and the K-Schur functions. So obviously I'm biased to the modified side. When the non-symmetric Macdonald polynomials came out, and it was known they hex symmetrized, so that's this arrow, to the Macdonalds, the question naturally is like, well, is there some modified version of the non-symmetric Macdonald that might have some of the interesting features that you have over here in the symmetric modified world? So that's a really natural question that over the years became even more compelling as more and more beautiful things arose around the modified Macdonald polynomials. Well, here's the history of the problem. Very early on, Knopp did find something a little bit like the funny positivity. Remember over here, there was that funny basis and that funny positivity that very beautifully mapped to the Schur positivity under the Garcia transformation. Knopp studied these guys and he discovered that if you like do some things like look at stable limits and find the right scalars, that he could come up with some positivity conjectures there. And then they sat standing still, and there was really not a lot of activity until 2019. And then Luc Lapointe started coming at it from the physics perspective, addressing similar questions. And then more recently, there's been quite a lot of work by Betzlaff, Weising, Goodberry, and Orr, not necessarily the question that I'm posing here, but more about particular stabilizations, because that's kind of what you have to do. Early on, as I said, it was understood that you do have to look at sort of stable versions of this guy on the left. Whatever, I'll say a little bit more later. And that's a lot of what their stuff has been done. They've been doing a lot of great stuff recently. Okay, so that's kind of where it was. And again, we're interested in this. So now I have to go back, all the way back to Catalan functions, which are symmetric. So this is another topic that is going to live in the symmetric world for a minute. And so in the 80s, that was when the harmonics module was there, and the harmonics module gave rise to this beautiful sum of Schur functions with Q coefficients, and then it led off to Macdonald, all the stuff we talked about. Well, another direction was some of the work that was done by Lustig. Basically, without the Q, this is a partition function, and the coefficients of Z without this Q here, right, were given as the partition function generating function of constant. And Lustig said, well, we can actually get Q weight, so you would get weight multiplicities by taking these, you could write the weight multiplicities as a signed sum of those. Lustig went further and said, well, if you put a Q in here, then you can get more information. And you can get this formula for Q weight multiplicities, which is like this signed sum of these coefficients. So this is just geometric series. If you expand it out, you get a positive sum, Q positive sum of these like Laurent monomials. And the coefficients of them, if you take a signed sum, give you the Q weight multiplicities. Whatever. So another way to look at Lustig's formula and this picture, which was a little bit of a different direction at the time, but more in the framework of what we've been talking about in terms of like Schur expansions, is that if you take this formula, right, and of course Lustig's interested in this thing, so are we. But anyway, by the way, he did this for like very, very general types, but I'm only sticking to the type A. So anyway, um, if you take this identity and you Weil symmetrize, essentially you just Weil symmetrize the identity. So this is the Weil symmetrization operator. But the thing about Weil symmetrization is that it converts a monomial to a Schur. But this is any vector. So it doesn't, if it's a partition, it definitely goes to a Schur function. If it's not a partition, it might introduce a negative. So anyway, if you Weil symmetrize this, well, times a monomial, then first you have to geometric expand it. Then you apply the Weil symmetrization. So each of these monomials goes to, well, some Schur function, but you might get a negative. And sometimes you get 0. But the point is, the coefficients of those are this sign sum. Because like, look at the Weil symmetrization operator. Essentially what it does is like converts, it gives you Lustig's formula as a coefficient of Schur. Well, Schur series, right? Because these are kind of funny Schur functions, right? They're allowed to have negative in their weights. They're just characters, it's fine. Now, hang on. So this is kind of a cleaner picture of what I was saying. If you take the partition function, which it's 1 over that, but I can put a monomial there, and you Weil symmetrize it, you get the Schur coefficient is this Lustig's formula for the Q8 multiplicity. But if you look at my example, so you get this thing, and those coefficients are what he wants, and it has negatives. But actually, if you kill these funny Schur functions, the one with negatives, like what is that? I mean, of course, it's something quite natural, but whatever. Kill the guys that have negatives, and look what you get in this example. This should look familiar to you. It was the example that we did in the very beginning, the sum of Schur function with tableau. So this is actually a Macdonald polynomial in a special case, just as Q's. And so the point is that this partition function, this Q partition function, if you Weil symmetrize it, leads somehow to a Schur positive sum. Now, it kind of makes sense for people who've now studied this Q multiplicity formula and they know it's Koska-Folk, whatever, that's fine. But still, by this definition that I showed you, all these negatives appearing really don't give you any reason a priori that you should have a pretty sum like this. Okay, but you do. And so at the time, this was intriguing to people. And they said, okay, well, if that does give you a Q positive sum of Schur functions, what happens if I change this product and don't take all of the roots, right? Instead of taking all the positive roots, which was what the Q8, the partition Q partition function was, take a subset of roots. And so sort of the earliest case of people experimenting with this beyond the case of all positive roots was Brouwer's work in 92. And this was like from a geometric perspective. He was looking at some special set of roots called parabolic roots. And the conjecture was that it was Schur positive and that you could prove it by some higher cohomology vanishing. And then lots of people sort of jumped in on that and they looked at different cases and like they were seeing all the Schur positivity and it was like really hard to prove. It was very, very hard to prove anything, even though people were attacking it from like lots of different ways, geometry, algebra, whatever. Okay, so on and on they're trying. And then around 2010, I think simultaneously, but separately, Chen, Haiman, and Panishev came up with sort of the master conjecture was that anytime your roots lie above a Dick path, so these are like root, each one of these is a lattice point. And if you use those roots up in that thing there, then you get sure positivity. So that was the conjecture. And we call these Catalan functions because, well, you have Catalan many of these Dicke paths. So if you take this expression up here, and this is roots underneath a Dicke path, the conjecture was that was Q sure positive. It included the case that had been studied by Lustig, which were the Koska-Folks polynomials or whatever. But it was okay, kind of complicated. Anyway, why the heck do I care? Because you know me, I only care about K-sure functions and Macdonald polynomials. So it's like, why do I care about this Catalan function stuff? Well, you can see the chart. You remembered how little progress we had with K-sure functions with the T. I started working with Jonah. He's the one that made me aware of Chen Haiman's work, and Anna Pun and Dan Summers. And we came up with a new definition of K-sure functions in terms of Catalan functions. And amazingly, that definition enabled us to prove that all the other definitions were the same, except for the very first one. That's still open, but I wouldn't go near it with a 10-foot pole. But anyway, whatever. So like, this is why I cared. It's amazing that one new definition could do so much for you. So this is just the quick summary of it. Catalan functions were, you take any set of roots underneath above a Dicke path. We found a really, really highly structured special Dicke path associated to lambda and k, and said that Catalan function is a K-sure function. And I'm not going to go into it, but the combinatorics of this path selection was just like so perfect that everything kind of fell out by like working with these roots and root expansions. So that was pretty awesome, especially because it had been so long. We were really excited about that. It helped us prove a lot of that stuff. And then we did dabble a little bit in saying, well, of course, when T is 1, this is a new formula. And we know that when T is 1, these are related to like the homology of the affine Grassmannian. So we looked at like some other, settings, and we studied in particular a K-theoretic version of Catalan functions. Now you have just like some lowering ideals in there, like you have 2 root ideals and something that makes it inhomogeneous. And anyway, we were able to prove some positive branching property for that. But really, Akita he had a conjecture that motivated us, and like they've really gone on and done much more than us. I mean, we did a little bit and then we kind of walked away for now. Anyway, so can't remember my point. Oh yeah, I'm getting there. I'm so sorry. I lost my train of thought. Okay, so whatever. This is not just like a brag session. It's actually going somewhere. So we discovered that this Catalan function stuff was really useful, and the Catalan function, or at least for K-sure functions. So we could prove K-sure functions, this particular Catalan function was sure positive. So then we were like, well, what would we do next? What about this conjecture that these Catalan functions are positive for any root ideal? And that we could not do with the techniques we use for K-sures. The techniques for K-sures were highly reliant on the path having a lot of structure. Now here is a conjecture for any Dicke path. But what we ended up doing to prove it was something that really inspired the work with the non-symmetric Macdonalds. And so just briefly, what we did was we went to a bigger set, kind of like the Knopp-Sahi idea. The Catalan function is that you use the Weil symmetrizer. But we started looking at not using the whole Weil symmetrizer, but just partially symmetrizing. So we took the same inside, and then we said, well, just partially symmetrize. Of course, then what the heck does this mean? Because that said, take a sure function that's ugly and throw it away. I don't have any Schur functions anymore because I've partially symmetrized. It's not even symmetric. But we have the key polynomials, which are like Schur polynomials for the non-symmetric world. And so this was important here, and it's important to our newer work, which is that it turns out that this truncation, you expand a non-symmetric polynomial into keys, and then you might have negatives because they're indexed by any integer vector, and you throw away the guys that have negatives. So that's all it is. If you have the key expansion, it's an easy operator, but unfortunately, getting some of these guys into keys is a little bit yucky, right? So I'm not saying it's easy. But anyway, that was what worked. And so that was kind of what enabled us to prove that the non-symmetric versions in particular cases were atom positive. And remember, that implies Schur positivity when you symmetrize. So the key tool here was that in the non-symmetric setting, there's a rotation theorem that allows for inductive techniques that you couldn't get when you restricted to the symmetric case. So anyway, we did that. Kato went on to do the geometric version of our sort of algebraic conjecture. And we have combinatorial formulas. So here I say two positive outcomes. I actually don't mean Kato's work, even though that is a highly positive outcome, but not of me. The other positive outcome is that we discovered, like I was trying to allude at in the previous slide, that this polynomial truncation of keys is like an amazing operation in its own right. So we define an operator that says, take any polynomial, divide by these powers that we've been seeing all over the place, and then take this polynomial truncation. So very similar to what we've been doing already. But now just think of it as an operator. And so when you go back to this long-standing mystery about non-symmetric Macdonald polynomials, the missing thing is that, well, since we don't have a really concrete funny positivity to just replace with nice positivity, you have to rely on knowing what that operation is. What is the operation to take you from the not modified sort of yucky side to the pretty side that has a potential for representation theory and K-Schur functions and Schubert calculus? And this operation that I just defined, well, you might think it's the right one and you apply it to the non-symmetric Macdonald, and then like you get something yucky and then you cry and go home and give up. No, of course you don't, because you wouldn't work in Macdonald polynomials or Schubert calculus if you were that personality type. So instead, you know that all these people have been doing amazing things with different stable versions of that. And so it turns out, now I know I'm like going over time, so I'll just like move a little bit more quickly, that if you take, we call it an R non-symmetric Macdonald. So instead of like non-symmetric, just the first R variables are non-symmetric, and then it's symmetric beyond that. But you can pick any R. But so it's like a refined, kind of a refined approach where you work in an R non-symmetric space. And when you take those Macdonald polynomials and you apply our operator, well, I computed an example at the bottom, and you start to see something really pretty, positive sums of monomials with Q's and T's. So that's highly suggestive that this guy could be the right operator. And so we define the image of one of these R symmetric Macdonald polynomials to be a modified R non-symmetric Macdonald. So we call it modern just because it's like an acronym. So this is like a modern Macdonald, modified R non-symmetric. And you see that it's positive here. And not only that, but we can complete this commutative diagram because when we looked at examples and applied the Vios symmetrization, we got an actual modified, which is Schur positive. So this suggested that our modern Macdonalds are atom positive and that they Vios symmetrize to the modified Macdonalds. So, of course, that brings a lot of questions forth. And then I'll just say, like, we do have a beautiful tableau formula, very much like the Macdonald polynomial formula. You, again, take tuples of tableau, but the only thing is now they're flagged. So each row has a maximum bound on the letter that you can get. So you get a finite number of them, and you get a non-symmetric Macdonald polynomial with the same Q and T. It's still the arms wiggling and the inversions. And so I guess I'll stop. Um, but anyway, so I hope like kind of the main thing for me is that like of course I have been obsessed and I have like a one-track mind about McDonald's and especially K-Shures, but I'm I'm trying to say, I don't know if successfully, that I really love that the ties that have come out of it with Schubert calculus, and now that we have this modified non-symmetric framework, I just don't see why there won't be amazing things related to Schubert calculus coming out of these non-symmetric modern McDonald's or whatever. So anyway, there's a lot of work to be done, and some people are already doing some great stuff. They're so fast. It's incredible. It's so humbling. Anyway, but thank you so much for listening, and I'm sorry to go over.
That was really great. Thank you so much.